Okay. We are good. The last topic. Right. You mentioned this word, this term yesterday, Abraham, quantum mechanics, yeah. So let's have a look at what it's all about. Now, we are only doing a very, very, very small part of quantum mechanics. And when I say a small part, I mean like, if the quantum mechanics book is 300 pages, we're doing page 1. Okay? So we're really just having a little look at it. Okay. So we're really going to focus mostly on hydrogen atom, be most concerned to us, and electrons as well. Okay, so you all know this formula. Whose formula is this? Newton, for the moon going around the Earth. We know this, okay? And then this one here, what's this one called? Do you remember the name of this one? Coulomb's law. Now, what do you notice about these two situations? Look at the formula. Kind of the same, aren't they? You both have a constant, yeah? You have an M1, M2, Q1, Q2, R squared. Moon around Earth, electron around proton. So you think that the situation should be similar. What I mean is, here, the moon can be in any orbit, correct? I mean, if we make the moon bigger or smaller, or the Earth bigger or smaller, we can change the orbit. Or if we make the moon go faster. Whatever. We can put the moon anywhere we want. It could be here, could be here, could be here, whatever. And we think the same should be the same for the electron. Maybe it's here, maybe it's here, maybe it's here, maybe it's here. So if you remember, I said that distance, there's no smallest distance. You can make the distance as small as you want. Remember I told you that? Well, I lied. Yeah. This is not true. There is a minimum distance. Okay. When you look at the hydrogen atom, it actually looks like this. That the electron can be here, 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 or here, but not in between. So these are like the orbits, the possible orbits. So firstly, draw this for me. Now you probably have seen this in chemistry. Yeah? Yeah. Ugh, spit on my coffee. Yeah? Right. Okay. Now, there's an interesting experiment here that actually shows that this is the situation. I mean, how do you know it's the situation? Well, we'll have a look at an experiment here. So, here is some light, and here is a prism. And you know, like a rainbow, when the light comes into the prism, you get all the different colours. You know this. Now here's a hot gas, and it goes through, like say the sun, you know, or a star, something like this. And the light goes through the prism, and you get this image here. Notice that you don't get all the colours. And then here you have the light through a cold gas. So like for example here, oh dear. Here we have gas, and then the light goes through the gas and then goes through the prism. And again, we don't get all the colours. We have some missing spots. You see that? Now, the reason for that, these situations, is because the atom is like this. What's happening here is that the electron, to move from 1 to 2, it needs some energy. And we learned yesterday that it can get the energy from a photon. And what controls the energy of the photon? What do you need to know to calculate the energy of a photon? Its frequency. Yeah? Make sense? So if this has the right energy, then it can move up a level. But then what happens to the photon? The photon disappears. The photon comes in, hits the electron, and then what happens to the electron? It moves up. Yeah, and the photon is gone. And that's what's happening here. When the photons come in, the photons of the right frequency, they get absorbed by the electron, and the electron moves up. That's why some of the colors are missing, because these are the frequencies the electron wants. This is what's happening here. Okay. Now you don't need to draw this, it's difficult to draw, but you can look at the video later again to have a look at the picture. But the names are important. So this one is called emission, and this one's called absorption. So what's happening here is some of the electrons are taking some of the photons and they're missing. Whereas this one here, we'll talk more about that one in a moment. Right now, this is the interesting one. So can you write this word down? Absorption spectrum. Now in fact, this is what you do in chemistry. This is called spectrometry. Spectrometry? Isn't it? Yeah. Isn't that what you do in chemistry? You take a gas, well, take a solid, you heat it to a gas, and then you shine light through it, and then you get this picture. And this is how you can know what the gas is, because different gases have different frequencies missing. So in fact, this is like a fingerprint. You know fingerprint? It's different for each gas. So this is how you can know what atom you have. Yeah? Does this make sense? Yeah? Okay, we'll go on anyways. So if electrons fall from a high orbit to a lower orbit, well, let's go back to this one here. So if I go from E2 to E1, do I gain or lose energy? Lose energy. So if I must keep the energy balanced, then that means a photon is made to keep the energy balanced. You know, like for example, here, when this falls, it loses energy in the nucleus here. When it falls, it loses energy. But the energy can't be lost, it can only be changed. So what happens is, as it falls, a photon comes out of the electron. This is what happens. And then the opposite happens. If a photon comes in and gives this energy, it will move up. If it gets enough energy, what will happen? It'll be free. What's this called? Sure, that's what, work function for metal ionization in chemistry. So I just wrote that down here. If an electron falls from a high orbit to a low orbit, then a photon will appear. If an electron in a low orbit gets a photon with enough energy, then it will absorb the photon and rise to a higher orbit. So this is worth making note of. Got that? Yep. Yeah. Okay. Here's a very, very, very small example, just to make sure we're clear about what's happening. So if an electron is in energy state 4 and it moves to energy state 3, and a photon is released, what is the energy of the photon? Well, it's simple. It's going to be the difference between this number and this number. So if I show you here, let me just minus 0.85 and minus 1.51. So you have it here. Here's my electron. And its energy here is, what did I say, minus 0.85 electron volts. And then here is the electron. And its energy is minus 1.51. Yeah? If the electron falls, it loses energy. How much energy? Let's calculate it. Uh, 66, is it? So it lost 0.66. But of course it can't lose energy. Energy must be conserved, must be balanced. So what happens to balance it is that a photon is released. Here's my photon, with frequency f. Anyway, all I'm asking you is how much energy this photon has, and the answer is it must have this much energy.
Energy is the electron.
Which energy? This the energy? This? This? Which? Yeah, what are you asking me? This one?
The whole thing is the electron.
This? In the picture?
Yeah.
Sorry. In the picture, this is an electron, this is an electron, and then this is a photon. Yeah? Okay. Now, the next question is similar, except this time I want to know what's the frequency of the photon. The frequency. I'm sorry, that should say minus, of course. Can you just make sure? So can you write down minus and this number as well? Here's the, oh yeah, EB. Okay, just write down the two numbers. Have you got them? Yeah? Okay, so let's have a look at it. Now, does it start in E1? Yeah. Okay, so what you have here, this is the lowest energy level. This is called E1. In fact, we call it the ground state, or the ground level. What's the energy in this level? Minus 13.6. And in a higher level, what's the energy? And what level number is it? Oh, the second level. Oh, okay. E3? Okay, doesn't matter really. 1.5? So if I have my electron here, and it moves up to here, it needs energy to do this. How much energy does it need? Can you calculate it for me? What's the difference here? What is it? Well, it gets energy when it goes up, so plus 12.1. Yeah. Now,
But we use minus 13.6 minus.
no, this one minus this one. The last minus the first. Yep. Now, where could it get this energy from to help it move up a level? From a photon. So the reason this happened is because a photon came in, hit the electron, and sent the electron up. How much energy does this photon have? Yeah. 12.1 electron volts. Can you convert to joules, please? What's that? 1.9 times 10 to the minus 18 joules. Now, what's the formula for energy of a photon? HF. So we have HF equals 1.9 times 10 to the minus 18 joules. Hold on there. What is it? 6.62. So what's the frequency now?
2.9 10 to the
It's fine. We'll do. So this is the frequency of the photon required. Yeah? Okay. Did you write this down? No. This is a common question in the exam actually, and it's, it's not in every exam of course. It's in a lot of exams. It's not too difficult. Got it? Yep. Okay. Back to the lecture. Okay, now there's a little video I want to show you, and in fact I think this has sound which will be nice. It's only like 6 minutes or something like this. Let me pause this, zoom in. So I'll just go back to the last slide. So this is the formula for the wavelength of the electron or any particle which is behaving like a wave, and now we're looking at this example question, and here is my answer so far. Okay, so what is the wavelength here? 2.4 times 10 to the minus 11, so it's quite small. Now the formula to calculate the angle is n lambda equals d sine theta. And here, what's the n? In fact, I don't think you needed to know this.
We can use the
Yeah, so I didn't need to give it to you. Okay, so the n is 1, the lambda is 2.4 times 10 to the minus 11, the d is 10 to the minus 10, and we have a sine theta. Of course, you shouldn't need to know the distance for the angle, it's just an angle. Sine theta equals 2.4 times 10 to the minus 11 all over 10 to the minus 10. So that equals 2.4 times 10 to the minus 1, which equals 0.24. What is this angle, please? Well, I would like degrees if it's possible.
13.8.
13 point, 13.8 you say?
Ask a question.
Hold on.
What's the
So again, Louise?
it says that H over M times this. But what's the figure for the M?
The M is the mass of the electron.
But the electron has the mass, is it?
Yes, it's on your card.
Okay.
Any other questions? No. 14 degrees. Like in the video. You saw the electrons make a fringe pattern. Yeah. I can go to the next slide. Yeah. Oh, actually, sorry, you do need the distance for the next part, which is what is the fringe separation. So, back to distance here.
1 meter.
We'll make it 1 meter, keep it easy.
What is the fringe?
I shall show you.
And
Oh, goodness.
It's the S.
Hold on, where's my pen gone? Pen. The S, the distance between the fringes. I don't remember the formula.
I think the length over WS. I think that's the problem.
Let's find out. Fringe separation. Fringe festival. Where are we? Yeah. So we have here, I'll switch it now. Slit separation, distance, and then fringe. Okay. So I would like to know this one. So I can get S equals D over D lambda, which is 1 over, what was this D here, 10 to the minus 10, and my lambda, 2.4, 10 to the minus 11. Yeah? So I have S equals 0.24, isn't it? Is that right? Yeah? So 24 centimeters apart, the fringes. Approximately. Yeah. Okay. Back to the slides. So here's some exercise questions for you. So what I'll do is, I'd like to try these for a few minutes and then we'll do a section B atom question. Actually, let me just, before you start it, ground. That should be a minus. And then for my question, I should have a distance of 1 meter. One meter away. Okay, let me open this up again. Where's my full screen? Full screen. Okay, so I'll let you try these for a few minutes. They're not very difficult, and in fact I mentioned a little bit about work function again, but we've done that yesterday. Okay, and this is the last topic. So I'll try these for a couple of minutes, and then I'll go get my physics book, and we will do some section B atoms question. I think, since we've just finished it, I think it'd be suitable.